All right, rational functions, which are just like big fractions. And you're probably thinking already, hey, couldn't we do those with the power rule? And you would be correct. A lot of times that's how it's going to go down. Other times though, there's exceptions like the natural log, which we'll go over. And I'll also have a video about natural logs, but I also want to emphasize that a lot of times these rational deals where you have a big fraction end up being natural log integrals. You don't want to forget about that 1 over u formula. All right, so let's take a look. First thing we're always going to try is power rule. So before we even write anything down, let's think to ourselves, hey, really this is just x cubed plus 4 to the negative 2 power. If I want to use the power rule, that would make this my u, x cubed plus 4. Do I have a du that's going to match up? We would look up here and we'd say, oh yeah, if we made u x cubed plus 4, our du would be like 3x squared. Oh look, it's going to work out perfectly. So now that we have a lot of confidence that this is a power rule, we'll start writing stuff down. As you'll see when these get harder, they don't always work out to power rule. Sometimes you got to do crazy stuff, so you do want to kind of check in your head before you start going crazy writing stuff down. So the derivative of x cubed is 3x squared. Oops, said squared, wrote cubed. Very hard to talk and write. All right, so there's our du. Awesome. So if I rewrite this problem, and sure enough, of course, 3x squared dx is up there, which means our u's match out. So I can rewrite this x cubed plus 4 to the negative 2 times 3x squared dx. There's my u, there's my du. So they integrate. So if you have a mathy teacher, they'll make you rewrite this problem as u to the negative 2 du. So just basically replace what we're calling u with an actual u, and then replace what we're calling the du with actual du. So now we'll have, what's the integral of u to the minus 2? Well, we raise the exponent by 1, and we divide by the new exponent, and add c to it. So we got negative u to the minus 1 plus c, which is really just negative 1 over u plus c, so that's negative 1 over, because after you get it in terms of u, they always want you to sub back in the x expression. So we'll replace u with what u equals, which is x cubed plus 4. And since it's just the first power, we don't need parentheses or anything down there. All right, pretty awesome. That's how they work a lot of the time. Let's see what else can happen. Now once again, I've got something with a power in it downstairs, so I'm thinking let's try the power rule. So just quickly in our heads, let's double check. Would this work out? If I make my u x squared plus 2x plus 4, is the derivative of that x plus 1? Well, let's see, it's actually 2x plus 2. But that's pretty close, so it looks like it's going to work. So if my u is x squared plus 2x plus 4, my du just needs to be 2x plus 2 dx. Now here's where it's going to work out. We have an x plus 1. We wish we had double that, 2x plus 2. So what we're going to do is just put a 2 right here that will distribute in to make that 2x plus 2. And then of course whenever you conjure a 2 out of nothingness, pull it out of your you-know-what, you got to put a 1/2 somewhere else to compensate. So this ends up being, and I'll rewrite this now as a positive power, or as a negative exponent to make everything one level so it looks more like a power rule problem. Yeah. So we have 1/2 times the integral of x squared plus 2x plus 4. And that's all. We're going to call that to the negative 4 power. That's what we did to bring it upstairs. And it gets multiplied by 2x plus 2 dx. All right, so at this point we got a good clean power rule situation. The du matches the u, so we'll be sticklers. We'll rewrite it as 1/2, and then we'll replace this u to the negative 4 with an actual u to the negative 4. And then all that 2x plus 2 dx stuff is just our du. So now it looks real pretty. It looks just like the integral formula, which has u's in it. So our new power is just 1 more. Remember, this is where it gets tricky. The negative 4th power, really you're adding 1 to it, which makes it negative 3. It's almost like a smaller exponent in a way, if you ask me, but hey. Then we divide by the new power, which is negative 3, and of course add plus c. So we still got our 1/2 out front. 1/2 times negative 3, though, is negative 1/6. And then u, we're now going to replace, actually, Maybe we'll just take that u to the minus 3 and move it downstairs, u cubed. And then our final step, we'll just replace u with what u equals using this equation here. We'll just substitute back in. So we'll get negative 1 over 6 times x squared plus 2x plus 4, and all that is to the third power. All right, so the interesting thing is, when you got a power downstairs, the power of the integral is actually smaller. We went from a 4 downstairs to a 3 downstairs. So it looks like the power got smaller, but really it got less negative, because in truth we went from a power of negative 4 to a power of negative 3. We added 1 to a negative 4, and that gives you kind of paradoxically a smaller number as your exponent. All right, here's another one. Not sure what to make of it, but you know, we've been on a roll here using the denominator as our u. So what would happen if we just said, oh, let's make u x squared minus 1. Our du would be 2x dx. Do I have that? No, I don't. This is kind of weird. I've got an x plus 1, which is almost like some extraneous stuff. If I didn't have the plus 1, that'd be great. I'd just have x times dx. So without the plus 1, it would actually match up nicely. Just multiply by 2, put 1/2 out front, we'd be done. But that plus 1 really screws us up. However, I would then look at this and think, doesn't x squared minus 1 factor? So yeah, let's factor this to x plus 1 over x plus 1, x minus 1. Because now the x plus 1's cancel, and we just get 1 here. So really it's just the integral of 1 over x minus 1. Now at this point, what's going on? We've got a situation. We can't just go around integrating x minus 1. Even though there's no obvious exponent here, really it's got a negative 1 power. This is really the integral of x minus 1 to the negative 1 dx. And that basically makes it a power rule. So even though downstairs it looked pretty benign, pretty non-threatening, because it was just x minus 1, didn't see any squares or cubes or anything, the fact that it was downstairs at all meant that it had a negative 1 power, thus we're in a power rule situation. So anytime you see something to a power, when in doubt, try using u equals whatever's to the power, so x minus 1. Du therefore equals dx. All right, so that's looking pretty good. We've got a dx match. So what is my integral? Well, let's substitute back in u to the minus 1, and dx is just du. So the same thing on this particular problem. And what is the integral of u to the minus 1? If you said u to the 0 over 0, hopefully you're scratching your head right now thinking, man, that's weird. That doesn't make a lot of sense. We did two illegal things. Well, we divided it by 0, which is obviously illegal in math. And then we also threw a 0 on the u, which means it goes away. It just becomes a 1. 1 divided by 0 doesn't seem like a very good answer. And that is correct. This is not a good answer. So remember, the power rule works for all powers. Roots, negative exponents, positive exponents, fractions, you name it. You can do it to anything except 1 over u. The integral of 1 over u du is the natural log of the absolute value of u. So the negative 1 power is the one power you're not allowed to use the power rule on. It's an exception. You got to do natural log. The way you spot it is, and the way I see students spot it all the time, so I've seen a million students over the years get to this point and freak out, or just kind of sit there quietly for a while, obviously thinking what the heck went wrong, double checking the work before that and all that kind of stuff. But the trick is, whenever you get, it's always the same. Whenever you do the power rule and end up dividing by 0, it's always the natural log formula. So you just want to take a step back and remember, oh yeah, that's natural log. And then just stick with natural log instead. So what we actually get is natural log of u, plus c of course. And of course at this point we could plug in, just substitute back in for u. So replace the u with what it was, which is not x squared minus 1 there. That's the one we did not use. We want this one, x minus 1. Boy, I managed to make that pretty messy. X minus 1, absolute value, plus c. We need the absolute value because you can't take the natural log of a negative number. It's undefined. So the way they get around that little peculiarity is they just put absolute values on everything. Whenever there's natural log, you want to throw on some absolute values. Pretty exciting. All right, here's another one that's more obviously a natural log again. So right away, we should be thinking to ourselves, oh yeah, that's just ln. So rewrite this. If u equals x plus 4, then du is just dx. So this is the integral of 1 over u du, which, as we saw a second ago, is just the natural log of u, which equals the ln of x plus 4 plus c. Alright, so that problem's exactly like the one we did a second ago. What about this one down here, though? This is pretty weird. I've got a lot of stuff going on. I got something above, something below. Now, as I mentioned before, you can't split this into two fractions. So we can't do that, or maybe it was in the end of the last video. You can't go around splitting this algebraically into two fractions. That's not going to work out. But what you want to recognize here is, when in doubt, and when you're having trouble figuring out what this is, because it doesn't really look like a power problem. Because we just have some exponentials, we have a big fraction. So it doesn't quite look like a power problem because there's no big exponents. But when you're not sure what rule to use, what you can do is just do some what ifs. So you can say, well, what if x cubed plus 4 was my u? What would my du be? You could say, what if 3x squared was my u? What would my du be? Now if you said, what if 3x squared was your u, then your du would be obviously not a fraction, so that doesn't work. But if we set up u equals x cubed plus 4, you notice that du is 3x squared dx, which is exactly what we've got up here right now. So that's setting off alarm bells like, oh hey, that must be our u. It can't be just a coincidence that that this u and this du would match perfectly. That can't be a coincidence. That must be the way they contrived the problem. So we're going to rewrite this as, and this is where u sub actually, the rigorous way of doing things actually pays off pretty good, because it'll make this look like a du over u. Just replace x cubed plus 4 with u, replace 3x squared with du, and hopefully it's setting off alarm bells that this is a natural log. And we end up with a natural log of x cubed, our original u, which is x cubed plus 4. Pretty nifty. So you can see that's kind of wild. When you think of the natural log equation, the integral of 1 over u being natural log, you don't usually think of u as having a bunch of exponents in it. But in this case, we had a cubed in it. It just wasn't, it wasn't the whole thing cubed, which would have been a power rule, because that would have been like a big -3 power on the whole denominator. What made this tricky was that you had x cubes within a 1 over u problem, because that x cubed is just one little part of u to the first power. So downstairs we really had u to the first power, just happened to have a cubed in it. But once again, when in doubt, just play a what if game. Hypothetically, if my u is the denominator, what would my du be? And if they match, you're looking at a 1 over u situation. All right. Well, what if our u and our du don't match up, and they just can't be made to match up? So, for example, this one, dx over x squared plus 4, it kind of looks a lot like the one we just worked. So my first instinct would be to say, well, there's a chance it'll work if I make my u x squared plus 4, then my du would be 2x dx. But you'll notice this one doesn't quite work out that way. There's no x upstairs. The 2 I can get. If I could just throw a 2 here, throw one out front anytime I want, that's no big deal. I can get the 2. What I cannot create, though, is that x. The x that's part of this du, there's just no way to conjure that. So I'm kind of hosed. I cannot make u and du match up on this problem for the power rule. But it turns out there's a couple of special formulas, and I obviously gave it away by putting them at the top of this page. But there's a couple of special formulas that help you out here. Now, you'll notice, so this one, it integrates to arctangent. Now, your class might not cover this. They might not use this formula, but if you're in AP, you should know this one. But just looking at this problem, just looking at this equation at the top, you wouldn't necessarily look at that and say, oh, that solves my problem. It still has du's in it. Oops, I should have put an integral sign. Slight omission. So it still has a du in it, so you'd think you'd still have the u problem, right? If your du wouldn't match for the power rule, why would all of a sudden your du work out perfectly for arctangent? Well, it turns out there's a reason. Is because in the power rule problem, this would have been 1 over u. So we have to have u equals x squared plus 4. But in the arctangent problem, we have u squared downstairs. So we're going to rewrite this as dx, just rewrite the original problem. That's really just, and you notice this is a squared and u squared, like they put the number first. Let's just do that. 4 plus x squared. Now I'm just going to rewrite this as a couple of things squared, because I want this to be a number squared plus a letter squared, right? So 2 quantity squared plus u quantity squared. So all I did was just rewrite x squared as, x in parentheses, squared, and I rewrote 4 as 2 squared, but I just did that to make the point really obvious that a equals 2 and u equals x, because the variable that's squared is x. So bingo. I've just got the perfect setup for arctangent, because now my u, instead of having x squared in it, when we tried to use the power rule, this whole denominator was our u, therefore our du had an x in it. But when your u is just x, that means your du is just dx. There's no x required, so all of a sudden it's not that bad that we just have a dx upstairs. That's all we need for arctangent. And that's where arctangent will save you if there's a problem you need to integrate, and one of the choices is not, cannot be done. There's a good chance it's arctangent. So basically anytime you see things squared downstairs, you want to be thinking, hey, maybe that's an arcsine or an arcsine or something, or an inverse tangent. And that's just kind of the way to spot it, is when nothing else works, maybe get lucky and it's one of the more esoteric formulas like these inverse trig functions. So if we at this point I just have all these letters that I can just plug straight in. So that what they've told me is that my du matches, because my du is just dx and that's what I've got. So now I just plug and chug. So the answer is 1 over a, so 1 over a, which is 2, times the tan arctangent, or tan minus 1, you can write it either way you want, of u, which is x, over a, which is 2 in this case, plus c. Pretty cool, right? So on the bright side, well, on the downside, it's something you have to memorize or whatever, be able to spot, but on the upside, it's really easy to plug and chug through the arctangent formula once you spot it. All right, so this next one looks pretty similar. It's got an x squared upstairs, and once again, the first thing you're going to think about trying is power rule, because yeah, you have a root downstairs, it's got a big power of x in it, so you're just thinking, hey, maybe my u is 25 minus x to the 6th. The problem with this is that the du then would be negative 6 x to the 5th. So I need an x to the 5th. But I've only got an x squared. Weird. Okay, so that's not going to work. But if you know your inverse trig function integrals, you might remember this puppy. The integral of something over square root of something minus something squared is arcsine. So let's try and plug and chug through that. If I want to rewrite this as something squared minus something squared, so I'll still have x squared dx upstairs. Not sure what to do with that yet. But then downstairs I'll have 5 squared. I'll just rewrite that 25 as 5 squared, because that sort of emphasizes that my a is equal to 5. And then x cubed squared would be what would give me x to the 6th, right? So I need something to square. All right, so at this point I've got a equals 5 and u equals x cubed, because that's what's being squared. That means my du is just 3x squared dx. Aha, now you see why having an x squared upstairs is not that bad. It actually works out for my inverse sine formula. The only thing I'm missing is a 3, so I need a 3 and a 1/3. So now I've got everything set. My du matches, I'm all good, so I got 1/3 times, now arcsine doesn't have anything out front, so it's just sine minus 1 of u, which is x cubed, over a, which in this case is 5, plus c. So you can see why you want to have that one in your back pocket, ready to pull out on integrals that don't work out right. Alright, so another trick they're going to make you pull sometimes is that the du's won't match up, and we'll have to use synthetic division or polynomial long division. So if you look at this one, what's going on with this one, it's pretty obvious right away this is not going to work with power rule or our natural log integration rule, because it's not a 1 over u situation. So if my u was x plus 1, my du would just be dx, not 2x squared. This 2x squared is sort of hanging out up here. It's not doing me any good. It's hurting me because it's making my du not work out for natural log. So I need another strategy. So what we're going to do is just long division. Now in the next problem we're going to do polynomial long division. On this one, because it's x to the first power plus 1, it's just x plus 1, there's no x squared or anything, we can use synthetic division. If you don't remember how to do synthetic division and long division, naturally on this website, if you go back to Algebra 2 or just search synthetic division, you'll find a chapter about synthetic division and polynomial long division. So you want to brush up on that if you're an AP or you got one of those teachers who's just kind of rough on you, it comes up surprisingly often that you'll want to be able to do synthetic division, or at least long division. Synthetic division is just a faster way to do polynomial long division. All right, so the way it works for synthetic division is you just take the opposite of this number. So if you have a plus 1 there, you actually put a negative 1 up here. Then for the numbers across the top, you're just going to put the coefficients here. So coefficient of x squared is 2. And then we can't just stop there. We got to include all the powers of x. So even though we don't have an x to the first power or a number, we just got to put zeros for those. All right, so you drop down that first number. Negative 1 times 2 is negative 2. Adds up to negative 2. Negative 1 times negative 2 is positive 2. Add those up to 2. All right, so what we're left with, this corresponds to 2x minus 2, and then this is our remainder, that 2. So it turns out that this integral is really the same thing as integrating 2x minus 2, and then a remainder of 2 over the original denominator. All right, so that might sound kind of crazy, except this is actually pretty integratable. You got a couple of polynomial type numbers, and then you got something that's going to be a pretty clean natural log. So the reason this was, it was a good idea to try synthetic division. This is an improper fraction. The power upstairs was bigger than the power downstairs, which meant that we'd end up with kind of a polynomial type situation. So if you want to integrate all this stuff, you basically got the integral of 2x minus 2. I'm just going to split it up into two integrals. Just to show you, because these two, those are just a polynomial that integrates really easily. But then this last thing is sort of its own beast, right? X plus 1 under 2, and we got a dx, of course. So this is going to integrate to a natural log. Because you notice that once again we have an x plus 1 downstairs. That didn't change. But this last term no longer has that 2x squared to worry about. So if u equals x plus 1 at this point, now du is fine. It's just dx. And that's what I've got. I mean, I have a 2 up there, which I can move out front. So I've just got a dx over x plus 1. So now all these should be pretty easy to integrate. 2x is going to be 2 times x squared over 2 minus 2x plus 2 ln of x plus 1, and of course plus c. So 2's cancel, so we get x squared minus 2x plus 2 ln x plus 1 in absolute value brackets plus c. Alright, so I'm not saying synthetic division is easy if you haven't seen it in a while. I'm just saying that that's one trick they throw at you. So if you're on a test, there might be 10 integration problems and one of them needs either synthetic division or long division. It seems like that's how teachers do it. There's so much normal stuff to test you on that they'll just throw a few trick problems in as well. So if you want to if you want to get an A, you kind of need to know how to do synthetic division or polynomial long division, one or the other pretty much. And then, but if you're just trying to pass, then you could just say, you know what, Chris, I really don't feel like doing synthetic division right now. If I miss one problem on the test, no big deal. I'd rather focus my attention on learning the integration instead of going back and spending an hour relearning how to do all that division junk. So it's really your call. And also it depends on your teacher. You could ask your teacher flat out, hey, do we have to know synthetic division? Or you could just be more direct, hey, will synthetic division or long division be on the test? And usually teachers will answer you. If they say something like, might be, or something, good chance you probably should get to know it a little bit. Alright, so here's another improper fraction. Now this one we're going to have to use long division because the denominator has an x squared in it. If it was x, we'd be fine, but x squared, all of a sudden we got to use polynomial long division. So we're taking x squared plus 1 into this mess. And again, there's some subtleties and ins and outs of long division, so if you don't remember this and you need it for your class, definitely go back and watch. So whatever we get on top here is going to be what we have to integrate. So x squared and x cubed is x times x squared is x cubed, and then plus x, and that goes under the x terms over here. So now we subtract all this stuff. X cubed minus x cubed, those cancel. 2x squared minus nothing is 2x squared, and 2x minus x is x. Carry down the 2. X squared and 2x squared is 2. 2 times x squared is 2x squared plus 2. Subtract all this mumbo jumbo. That cancels, and we get x. And that's it, just x. All right, so our remainder is x, and our answer is x plus 2. So this integral is equivalent to x plus 2, just flat out, no fractions or anything, and then plus our remainder, which is x, over x squared plus 1. And of course all this is times dx because we always need a dx, right? Otherwise you wouldn't be integrating. All right, so this is another one that's pretty straightforward. X plus 2, very easy to integrate. X squared over 2 plus 2x. But then we've got the integral of this x squared plus 1 under x thing. All right, so this one's a little bit juicier than last time. X squared plus 1 looks like it's probably my u. Let's see what happens. So if u equals x squared plus 1, my du is just 2x dx. All right, so that's going to work if I just put, I need a 2 here, which means I need to put a 1/2 out front. But now I've got that, what does this rewrite to? So it's got x squared over 2 plus 2x plus 1/2 times the integral of du over u. So what is du over u integrate to? That's right, it's another natural log. Natural logs, even though they don't show up that often, in any math class you've had before, like pre-calculus, you already knew what natural logs were, and yet they almost never came up. But in calculus and integrals, they show up all the time, just because anytime you're integrating 1 over something to the first power, it ends up being a natural log. So they actually show up very frequently. So it's x squared over 2 plus 2x plus 1/2 times ln of absolute value of u. And now we just got to get rid of the u by putting in the original. Actually, I don't know if you have to do this. You probably don't have to do this, but I'm going to convert the bars, the absolute value bars, back to parentheses because x squared plus 1 is always positive. There's no way to have an x squared that's negative, right? And positive 1 is always positive. So that means I don't need the absolute values. You could leave them if you want, but it's just kind of something worth remembering. So you want to keep your eye out for, like, if the absolute value bars are there, why are they there? And when can you take them away? And x squared plus 1 is always positive, so we don't need them. All right, so that's rational. As you can see, the power rule is kind of like just the start of it. A lot of work on matching your u's and your du's. If that doesn't work, start thinking about crazy stuff like synthetic division and long division. It's just unfortunately with rational expressions, a lot of times you're going to be staring at it wondering, oh man, my du's don't match. What else should I try? And hopefully this video gave you a bunch of ideas for what to try when that first shot you take doesn't work out.